have a new topic, concavity. And when we talk about concavity, we're talking about whether the graph is smiling or frowning. That's how I always think about it. When we talk about concavity, we're talking about kind of an opening up, or is the function opening down? So when we talk about concavity, we now have to talk about a differentiable function being concave up on an open interval if the derivative is increasing, and concave down if the derivative is decreasing. So I want you to think about, we're talking about the slope graph having a positive slope. We're talking about slope of the slope. And again, slope of the slope. So what do we think of when we hear slope of the slope? Well, what we're looking at then is this definition down here in another way of looking at it, and you can even connect these. I would just kind of draw an arrow that these are connected. It's concave up when the second derivative is positive, and when the second derivative is negative, the function is concave down. They are saying essentially the same things. So if we look back at my favorite function, y equals x squared, y equals x squared is the most basic quadratic function, and it's always smiling at you. It's always a happy function. So we would say that y equals x squared is concave up on the interval of all real numbers. You can use a double-barreled R there, because its second derivative, blank, is always blank. So we had this function, y equals x squared, and they want us to find the second derivative. Well, the first derivative is 2x. So then the second derivative is 2. And 2 is always positive, which guarantees that that function is always concave up. So let's look at example 4. We're going to talk about the concavity of 3 plus sine of x on the interval from 0 to 2 pi. I'd like you to take a second and sketch a picture of what 3 plus sine of x looks like. This is just the graph of sine of x shifted up 3. So it still looks like this. What I want you to notice is you can just look at the picture and kind of determine it, but we're going to do it algebraically as well. It's a sad face here, and there's a happy face here. So somewhere in here, it switches. So according to this second derivative test, this concavity test, it says we need to find the second derivative and show when it's equal to 0. So the first derivative of sine, is cosine. So then the second derivative of cosine, is negative sine of x. And we want to know, where is that equal to 0? Well, if we divide by the -1, we get sine of x equals 0. And we know that sine of x is 0 at x equals 0, x equals pi, 2 pi, etc. But we only care about the window from 0 to 2 pi. So now we have to actually test those points. I don't have to go beyond 0 and 2 pi. So pi is in the middle. I really only have to check 2 intervals here. We got these values from the second derivative. I guess I should have put y double prime, but that means I'm going to test points in the second derivative. So if I test a point between 0 and pi, I choose pi halves. When I plug in pi halves to negative sine of x, sine of pi halves is 1, so -1 means this one is negative. And if I plug in a number between pi and 2 pi, I pick 3 pi halves. Sine of 3 pi halves is -1, so -1 is positive. So the second derivative was negative from 0 to pi, and according to our definition, if the second derivative is negative, that means that the function was concave down. So my conclusion is y is concave down from 0 to pi and y is concave up from pi to 2 pi. So what you just found here, 0, pi, and 2 pi, it's our next super important definition. Take out those highlighters. A point of inflection. It's similar to a critical point, but this time we're talking about the second derivative. So the point of inflection definition, it says it's a point where the graph of a function has a tangent line. That's an important piece of information. It means it's differentiable. And where the concavity changes. So it changed at pi. So we would call that a point of inflection. So the second derivative test helps us out now with these very specific definitions. If f prime of c is 0, that means there's a critical point. And if f double prime of c is less than 0, that means it's concave down. And when I'm saying it, I apologize, it should be f. That means f is concave down. So we have a critical point, and the function is concave down. That's going to guarantee us a maximum. We're talking about concave down, and there's a critical point, which means the slope is 0. So this point right here would be considered a maximum. The opposite is also true. Critical point, concave up, guarantees us a minimum. Now, this is the exact same function you already did in example 2. So we already know the answers here. We're going to use the second derivative test. First thing we need to know is where the function's derivative equals 0 and where the second derivative is greater than or less than 0. So take a moment and find both derivatives, find the critical points and the inflection points. All right, here's our information from example 2. The critical points were at plus or minus 2. And if I find the second derivative equal to 0, that's our point of inflection. So now what they want us to do for the second derivative test is they want us to figure out at these two critical points, what is the second derivative doing? So I want to know what is the second derivative at negative 2 and what is the second derivative at positive 2. Well, at negative 2, it's negative 12. 6 times negative 2 is negative 12. 6 times positive 2 is 12. So according to this definition, if my second derivative is negative, that guarantees that I have a max. And my second derivative was positive, that guarantees I've got a min. So I can rewrite those ordered pairs by plugging back into the original equation. All right, I want you to work through example 6. I will help out with the graph at the end, but I will pause this and have you work through example 6. One thing I want to make sure you note, and I would even highlight this in your notes, is that this one is talking about f prime of x. They already gave you the first derivative. So I set the derivative equal to 0, and I factored out a 4x squared, and I found that x equals 0 and x equals 3 were my two critical points. But then when I did my sign chart, I noticed something that I haven't seen before. I got negative, negative, positive. It didn't change signs here. So I have a critical point, but it did not result in an extreme value. I don't have a max or a min. It just kind of flattened out. So it was negative, flattened out, negative, then back to positive. So the only thing I do know is there's a min at x equals 3. I don't know the y value because I don't have a function. All right, here is the rest of the information. I want you to use this information to help graph f. We're going to go over that one in class.